In this video, I'm going to demonstrate how to graph a rational function in the Connect Math and ALEKS systems. So before we get started graphing, just a few pieces of general advice anytime you graph a homework problem. First piece of advice is, of course, make sure you read the directions really carefully. Sometimes the graphing directions are fairly vague. They leave a little bit open-ended. But in the case of a function like this, the directions are very specific. So you're going to have to make sure you follow the directions very carefully in order to make sure that the system graphs the function correctly. So in this case, notice it says we need to plot all necessary asymptotes. So any asymptotes this function has, vertical, horizontal, slanted, we need to make sure that all of those are graphed. And then also notice that it says for vertical asymptotes, we want to make sure that there are at least 2 points on each side of each asymptote. So what that means is that if we have one vertical asymptote, we'll need 2 points to the left, 2 points to the right, 4 points in total. If we had two vertical asymptotes, for example, we'll need 2 on the far left, 2 on the far right, and 2 in between the asymptotes for 6 points in total. So just make sure as you graph that you have 2 points on either side of any asymptote, or specifically any vertical asymptote that you graph. So first piece of advice, make sure you read the directions very carefully. Now, second piece of advice is I want you to make sure that you work this problem out on paper before you try to input your graph into the system. And there's a couple reasons for doing that. The first reason for doing that is, of course, you need to make sure that you can graph by hand. You won't always be graphing on the computer, so you need to make sure that you can do this by hand as well. The other reason that it's important to work the problem out on paper first is if you make a mistake while you're graphing, it's going to be very difficult to find where that mistake is if you don't actually have any work written down. So the work written down is going to allow you to figure out if there's a mistake, if something goes wrong when you attempt to graph and connect the points at the end. So number two, second most important thing is make sure that you work everything out on paper first. Okay, so let's get started graphing and then we'll go from there. We'll determine if anything else needs to happen. And again, I want you to do everything on paper first. So our function here is r of x is equal to 5x plus 3 divided by 3x minus 7, and we want to graph this function. So give me a moment, let me toggle between a couple of screens. Okay. So let's get started graphing. I've written down the function. We want to find all the asymptotes for this function, and then also it's ideal to find your x and y intercepts if the function has any, and then we'll see if we need any additional points beyond that. So let me start with my vertical asymptotes. Now, as we know with a rational function, the vertical asymptotes are going to come from the denominator. So any value of x that makes the denominator 0 corresponds to a vertical asymptote on the rational function's graph. So if I want to find my vertical asymptotes, I'm going to start by setting my denominator equal to 0, and then I'm going to solve for x. So if I add my 7, divide my 3, I'll get x is equal to 7/3. So that's going to be the equation of my only vertical asymptote, and we'll put that on the graph in just a moment. Now I also need a horizontal asymptote. I want to see if I have any of those. So remember, for the horizontal asymptotes, we're going to compare the degree in the numerator and the degree in the denominator. So remember, that means what's the highest exponent on x in the numerator, what's the highest exponent on x in the denominator. So in the numerator, our degree, which we call n, is going to be 1. The highest power of x is 1. In the denominator, the highest power of x is also 1. So in that case, we fall under the situation where our numerator and denominator's degrees are the same. And if you remember, if that's the case, then we do have a horizontal asymptote, and specifically, it's going to be of the form y is equal to, and we're going to have a constant in order to have a horizontal line. And the constant specifically is going to be the ratio of the leading coefficients, those coefficients associated with the term from which we found the degree. So in that case, our horizontal asymptote is going to be located at y equals 5/3. So you'll notice that both of these asymptotes are going to fall at fractional values, and that's one of the reasons I chose this particular problem to work. I want to show you what's going to happen when your numbers aren't necessarily integers and they're not ideal numbers to graph. So those will be our asymptotes. We'll put them on the graph in just a moment. Now I want to go through and I want to find my intercepts. So my x-intercept, my y-intercept, if this function has either of them. So for my x-intercept, I know I'm going to let y be equal to 0, and I'm going to solve for the corresponding x. So in that case, y is the same thing as r of x in this case. So we're going to take the whole function, and where I see r of x, I'm going to replace it with a 0, and we're going to solve for the x that makes this true. Now, in order for a ratio of two numbers to be equal to 0, the numerator has to be 0. So in order for this equation to be true, we also have to have 5x plus 3 equal to 0. The only way this ratio of two numbers comes out to 0 is if the numerator is 0. So I can set my numerator equal to 0, and I can solve for x, and that represents my x-intercept. So it's very similar now to the equation we solved with the vertical asymptote. I'm just going to isolate my x. So I'm going to subtract 3, divide 5, and we get x is equal to negative 3/5. Now this is not an asymptote. Remember, this is a coordinate associated with the x-intercept. So that means our x-intercept is going to be negative 3/5, comma, 0. So that'll be the one location this function's graph crosses the x-axis. And then I also want to finish up by finding the y-intercept. So we're going to let x equal 0, which means using function notation, we're going to replace x with 0. So we're going to evaluate r of 0, which means sub in 0 in place of x, and then simplify from there. Okay, so in this case, my first two terms go to 0. So I'm left with 3 divided by negative 7, or negative 3/7. So this is going to be the y-coordinate of my y-intercept. So my y-intercept is the ordered pair 0, negative 3/7. Okay, so now let's put all of this onto the graph by hand, and then we'll translate that into a graph in our homework system. So I'm going to start with the asymptotes. Now again, notice that these asymptotes had fractional values. So when we graph them on the coordinate plane by hand, we're probably going to have to do a little bit of approximation, and that is perfectly fine. Now, when we translate this into the homework system, approximation is not going to cut it. So my third piece of advice for graphing in the homework system is make sure when you're doing things online, you're only using exact values. You cannot use approximated values in the system, because ultimately what the homework system is doing is it's taking all of the pieces you input and it's matching them to whatever unique function has those specific characteristics. So if you use an approximation rather than an exact value, like 7/3 or 5/3, it's going to try to match a function to those approximations, and it's not going to come up with the correct function. So you're going to need to use exact values like 7/3 and 5/3, and of course I'll show you how to do that. But when you're doing things by hand, approximation is perfectly fine, and ultimately it's going to be necessary. So our vertical asymptote fell at 7/3, so I'm going to type that in, get an approximation. So that's about 2.3. So our vertical asymptote falls a little bit between x equals 2 and x equals 3. So just ballpark it. It doesn't have to be perfect, just as long as your vertical asymptote is between x equals 2 and x equals 3. Okay, now our horizontal asymptote fell at 5/3. So if I approximate 5/3, that's going to be 1.67. Okay, so between 1 and 2, and again that's a horizontal asymptote, so between 1 and 2, but a little bit closer to 2 than to 1. And again, just do your best, just ballpark it. Just make sure you're between the correct coordinates. Okay, so there's our asymptotes. Okay, now remember we need 2 points on either side of our vertical asymptote. So we'll need 2 points to the left of that asymptote, we'll need 2 points to the right. So the intercepts represent at least a couple of the points that we can use to graph. And again, those are fractional values. When we put them in online, we're going to make sure we do it using exact coordinates, but here it's perfectly acceptable to just approximate those. So our x-intercept was at negative 3/5, and if I approximate that, that's negative 0.6. That's actually not an approximation, it's just a decimal version of that number. But ultimately, it's between 0 and negative 1. So we cross the x-axis between 0 and negative 1. A little bit closer to negative 1 than to 0. Okay, now our y-intercept is at -3/7. If we get an approximation for that, about -0.4. So we cross the y-axis between 0 and -1, a little bit closer to 0 than to -1, so somewhere around there. Okay, so that gives us our 2 points to the left of our vertical asymptote. Now we need to find 2 points that are to the right of the vertical asymptote. So there's a couple of different ways to do that. I want to show you a way that you can do that where you can use the graphing calculator to save yourself a little bit of time. So you're actually going to use the graphing utility in the graphing calculator. So go to y equals, and you're going to type in your function. Now there's a couple of different ways to type this in. If you just want to use the division symbol to represent the fraction bar, you can certainly do that. If you do that, I want to caution you, you need to make sure you have parentheses around your numerator and parentheses around your denominator separated by that division symbol. If you leave off those parentheses, then the calculator is not going to interpret what you typed the way you want it to, and you won't actually graph the same function that we're graphing here. So make sure if you use the division symbol, you put parentheses around your numerator, parentheses around your denominator. The TI-84 also has a way to format fractions, so if you've never done that before, it is associated with the y equals button. Notice in green right above it, it says F1. That's where you're actually going to find fraction formatting. So because it's in green, you access it using the alpha button first, so alpha, and then y equals. And then notice it brings up a menu of all the different ways you can format a fraction. So option 1 is just plain old fraction, numerator, denominator. Option 2 would be a mixed number. If you want to have a whole part and then a fractional part, you can type that as well. So we're going to use option 1. I'm going to press enter, and notice it formats a numerator and denominator. If you formatted it this way, you don't need to worry about those parentheses. So I'm going to type in my numerator, which was 5x plus 3. And then I'm going to type in my denominator. Oops, looks like I made a mistake. I think that's a 2. Let's fix that. 5x plus 3. There we go. And then our denominator is going to be 3x minus 7. Okay, double check everything before you hit enter, before you graph it. Make sure it looks exactly the way it needs to before you proceed. So once we're satisfied, we can hit the graph button, and that's going to give us a sense of shape. And already that seems to make sense with what we have. It looks like our horizontal asymptote is above the x-axis. Our vertical asymptote is to the right of the y-axis, so that at least makes sense with what we have on the graph so far. Our intercepts look like they're roughly correct as well, so that's a good thing. Now what I really want beyond the graph is the table. I want to use the table function here. That's where we can get some other coordinates that can save us a little bit of time when it comes to graphing. So I'm going to go second graph, and I'm going to open up the table associated with this graph. Now, depending on the values you have for your intercepts or for your asymptotes, you can actually look for those values here in the table. So notice here at 0, we have 0, -3/7, and that was our y-intercept. So that confirms that that value was correct. Now we're not going to be able to find the x-intercept in the table as it stands because it's associated with a fractional x value, and our table is only set up to show integer x values, so you won't be able to identify that there in this table. In some cases you can also identify the vertical asymptote. If you find an x value that corresponds to an error in the y column, that means that's the location of a vertical asymptote. Now again, we're looking at a fractional x value for the vertical asymptote, so again, it's not going to be represented in this table, but if it were, that's how you would identify it. Now what we really want here are extra values to graph. So notice where our vertical asymptote fell. It fell between 2 and 3. So we need values probably larger than 3, x values larger than 3 that we can use to graph so we can get the 2 points to the right side of that asymptote. And this is where the table saves us some time. So I see an ordered pair at 3, 9, identified from the table. So that will be a point that we can add to the graph that'll give us extra points in the section where we don't actually have any graph yet. So 3, 9 is going to be one of the ordered pairs on our graph. And then I also need another point further to the right than that. And if I can find some good values, I'll use them. Notice we see a 6, 3 as well. Now, if for example we didn't have something like 6, 3, and maybe that 3, 9 was the only ordered pair where we actually had whole number values. We actually had integer values. What can we do? Well, in this case, the table's formatted where we can actually see some fractions, but suppose that it weren't. Your table may be set up so that when you type in your function and you graph it, you see 4 and then a decimal. Well, more than likely the decimal you see is going to be an approximation of whatever that number happens to be. And again, we're not going to be able to use approximations online. So ultimately, the question is, what do you do when the numbers in the table just aren't great numbers? They're not good numbers for graphing with. What you're going to do in that case is you're going to have to generate some of the ordered pairs by hand, and I want to show you how you can do that. Essentially, you'll do the same thing you did when you found the y-intercept, but you'll pick another value for x other than 0. So suppose, for example, we wanted to graph an ordered pair associated with x equals 4. Well, if I want to do that, all I do is pick that value of x, and then I'm going to evaluate r of that particular value of x. So rather than plugging in 0, in this case I'm going to plug in 4. So I'm going to take my function, take its rule, and then substitute in a 4 in place of x. So that'll be 5 times 4 plus 3 divided by 3 times 4 minus 7. Now I want to simplify my numerator, simplify my denominator. So 5 times 4 is going to be 20. 20 plus 3 is going to be 23. And then in my denominator, 3 times 4 is 12. 12 minus 7 is going to be 5. So 23 over 5, which matches with what the table has given us as well. So another ordered pair on this graph would be 4, 23 over 5. And again, we can actually see this from the table, but the reason I wanted to show you that is depending on how your table is formatted, you may have decimals rather than fractional values. You cannot use those decimals when you graph in Connect Math or in ALEKS. So you're going to need to make sure you have fractional values. If you need to find fractional values, that's how you're going to do it. Now, 23 over 5, let's see what that is as an approximation. So we'll quit, we'll get out of there. 23 divided by 5 is 4.6. Okay, so 4.6 is on our graph. So 4, 1, 2, 3, 4, between 4 and 5, a little bit closer to 5, and there's our point. Okay, so we have 2 points to the left of our vertical asymptote. We have 2 points to the right of our vertical asymptote, and if we go back and look at the graph, essentially we know the shape. The shape is going to follow our horizontal asymptote from below, and then our vertical asymptote to the left-hand side. And so we'll have one branch of the graph that follows through those points, hugs those asymptotes, and then we'll have a symmetric branch of the graph that goes through these points and follows the asymptotes from the other side. Okay, so graphing by hand, that's roughly what we expect. It's not perfect, but it's fairly accurate, and we have the algebra to back it up. Now what we want to do is we want to translate that into the homework system so that we can graph this digitally, and ultimately when it's graphed online it should look the same as what we have, number 1, on the calculator, and number 2, on the paper when we graphed by hand. So I'm going to switch over to the online homework system, and we're going to input all of those features. Okay, so I like to start with my asymptotes. So our vertical asymptote, if you recall, was that x equals 7/3. Now, first off, let's take a look at the grid. Notice we have a scale of 2, so we're counting by 2. We're not counting by 1 on the grid, we're counting by 2. So 7/3 is not going to be a number that's easy to identify on a grid where we're counting by 2. So if it were, here's what you would do. You would use your pencil, you can drop points using the pencil, or you use the vertical asymptote tool to immediately drop your asymptote where it needs to go. So when you're working with integer values, that's how you'll drag and drop your asymptote. Now, if it's a situation like this where we don't actually have an integer value associated with our asymptote, what we're going to have to do is we're going to have to use the point plot tool in order to plot a point that our asymptote can then snap to. And notice it mentions that in the directions. It says use the plot point tool for non-integer coordinates if necessary. So this is going to be a situation where we need that. So this is going to be your point plotting tool. looks like a little coordinate plane with an X. If you click that, it's going to give you a box where you can type in fractional coordinates that you can't just drag and drop to on your grid. So we want to graph a line at x equals 7/3. So all we need in order to snap to that location on the grid is some point that would be on the line. Well, what's an example of a point that would be on the line x equals 7/3? Well, for example, 7/3, 0 would be on that line. So if I type in the ordered pair, 7/3 and 0, and then click plot point, we don't see anything yet because the window's blocking it, but if I close that out, notice it plots a point that fell between 2 and 4. And then I can take my asymptote tool, and it snaps to the grid, but it also snaps to that location as well. So I can click and I can place my asymptote. And that's going to be an accurately graphed asymptote. Now let's do the same thing for the horizontal asymptote. It fell at y equals 5/3, which again we can't locate here on the grid based on a scale of 2. So I'm going to use the point plotter. We need a point that would fall on the line y equals 5/3. So an example of a point that would fall on that line would be 0 and 5/3. So I'm going to plot that point, and then I'm going to use my horizontal asymptote tool, snap to that location, and then I have my horizontal asymptote graphed. And those look essentially like what we graphed when we graphed by hand, and also what was on the graphing calculator. Okay, now I need to add in my ordered pairs. Remember, 3 of the ordered pairs we found had fractional values associated with them. 1 of them had integer values. So the one that had integer values was 3, 9. Anytime we have a point that has integer values, we can typically graph it just using the pencil. In other words, just drag and drop. So even though our scale is counting by 2, it can typically graph half values as well. So for some reason my pencil's not showing up. Let's see if I can get it to show up. No, it doesn't want to show up. But essentially, if you just take the little crosshairs and drag and drop, you can put a point where you want. So we want to point at 3, 9, so halfway between 2 and 4, and halfway between 8 and 10. So if I drag and drop in the middle, notice it puts it right in the middle. So it'll give you essentially halfway values between your grid lines, but something like a third or a fourth, you're not going to be able to get there. You'll have to use the point plotter. Okay, now for the other values, we are going to have to use that point plotter. So I'm going to open it up, and we can actually do the other 3 points all in one. You can plot 3 points and then close out the window, and it will have plotted all 3. So let's start with our x-intercept. So our x-intercept was at -3/5, 0. So we need our negative sign. We'll put in the fraction. So -3/5. Oops. And then click over, and then 0. I'm going to plot that point. Okay, and again, it's there. You can close the window if you want to confirm that, or you can just plot your other 2 points. So the next point is at 0, -3/7. So 0, and then negative, and put our fraction, 3/7. Oops, 3/7. There we go, plot that point. And then our last point was at 4 and 23/5. So 4 for the first coordinate, second coordinate we need a fraction, 23/5, plot that point, and then you can close that. And notice it's plotted all of those points. Okay, so essentially everything we found algebraically is now on the graph. And what we're going to do once we have all the points and all the features graphed is we're going to use the graph a function tool, and that's going to connect the dots. And ultimately, the shape you see should match up with what you graphed by hand, number 1, and what you saw on the graphing calculator, number 2. Okay, so once we're satisfied, we'll click the check answer button. And it looks like I timed out. But regardless, that was the correct one. It'll mark it right if it's right. It'll mark it wrong if there's a mistake. Now, I do want to mention what happens if maybe you connect the dots, you use that graph a function tool, and something just doesn't seem to work. Something's not working. The graph shape doesn't seem to be matching up with what you expect it to look like. What that typically means is one of two things. Number one, it could mean that you didn't plot enough information. So again, it said you need 2 points to the left and to the right of your vertical asymptote. Maybe you plotted 2 to the left but only 1 to the right. If that's the case, then more than likely the system will not have enough information to generate your graph. So you need to go back in and you need to make sure all the important features of your graph are there in order for the system to accurately graph it. Now, if everything is there in terms of just the amount of information, yet your graph is still wrong, typically what that means is that one of your coordinates is wrong, or maybe the location of one of your asymptotes is wrong. So probably the most common mistake starting out is you forget that you can't use those approximated values. So something like 0.33, you cannot use that in place of 1/3. You have to use 1/3 instead. So if you used any approximated values, you need to go back and you need to fix those because the system does not recognize those. And again, that's one of the reasons why you put everything on paper, because if approximation is not an issue, odds are it means one of your ordered pairs is wrong. So go back and check your work, make sure you didn't make an arithmetic mistake, fix any mistakes you see there, and that should fix the graph for you. So there you go, graphing a rational function in Connect Math and ALEKS.